5.3 is on page 252, talks about solving systems and higher order equations numerically. They talk about the Euler method, Ranakata method. We're going to focus on the normal form. That's what we're going to need when the time comes. A system of m differential equations and the m unknown functions can be expressed as a first order in each of those. Now, if it has a higher order than that, you could still set it as a first order, and that allows you to solve it. If you could do that, we call that the normal form. Notice that equation 1 has m first order equations, and that collectively looks like a vectorized version of a single generic first order equation. It looks something like that, where you have it in terms of t and some multiples of x. Now you take the initial conditions, you could alter those as well to match, and you get yourself one of those systems of first order differential equations. And we're just going to play with that in this case. That's all we're going to do. We did solve it in another course, but here they don't really get into the solving at all. So this is on page 259. So the idea is fairly simple, but it allows you to solve higher order, second, third, fourth, fifth order, and so on and so forth. These things are very useful. So if I look at number 2, what you do, you convert that to x. You say, you know what? Let x sub 1 equal y. And what you do, you take a derivative. You let that equal x2. And what you do, you keep on taking derivatives until you get all the derivatives possible. So I could keep on doing this forever, but here I just need to go as high as a second derivative because that's a second order. So if I replace that equation by what's given, I know that x1 prime is x2. It's right there. And x2 prime is cosine of t minus, but y is x1 plus y squared, that's x sub 1 squared, and that's the system they're talking about. It's going to be in terms of first order differential equation on all of those, and this is called a normal form, a massive deal. If I look at the second problem, that's a bit more than the first one. Well, let's see how this works. I'm going to come in and say let x1 equal y. I'm going to take a derivative. Call that x sub 2. Take a derivative of that. Call that x sub 3. I need to go all the way to 6. Take a derivative of x3, that's y triple prime. Take a derivative of x sub 4, that's the fourth derivative. Call it x sub 5. Take a derivative of x sub 5, that is the fifth derivative. So in this case, I need a derivative of 6 of those to match, and that's always the case. So here I would say, well, let's see. In our case, we let x1 prime equal x2. And we let x2 prime equal x3, and x3 prime equal x4, and x4 prime equal x5, and x5 prime equal x6, and here comes x6 prime would be, let's see what that is. That is going to be negative y prime was x sub 2 cubed minus the sine of y, and y was x sub 1 plus e to the 2t. And believe it or not, this system is we could solve this using matrices. For now, that's all we're doing. We get to a system that has kind of like 5.2, 2 by 2. You say, okay, well, no big deal. Let x sub 1 equal x in this case. Take a derivative. X sub 1 prime equal x prime, and that is called x sub 2. X sub 2 prime equal x double prime, and that's the highest they have. So for now, this is what I have. I have x sub 1 prime equal x sub 2. I have x sub 2 prime equal, well, x sub 2 prime equal, if I move this to this side, that would be negative 5 over 3 x, and x is x sub 1, right? Plus 2 over 3, there's a y. Well, I'm not on the y's yet because I'm going to go on and continue. I'm going to say let x3 equal y. And if I take a derivative, that's going to be y prime, call that x sub 4. And I'm going to take x sub 4 prime to equal y double prime. I'm going to stop there. So now that I have this y, that's in terms of x sub 3. And I'm going to go ahead, there's x sub 3 equal prime equal x sub 3 prime equal x sub 4 right there. And the last deal, when I get to x sub 4 prime, which is y double prime, that's going to be, if I move that to the right, that's going to be positive 6 over 4, 3/2 x, x was x sub 1, minus 2y over 4, that's 1/2 y, and we let y equal x sub 3. And that's the system we're talking about. Oh, I almost forgot the initial conditions. Oh boy. Okay, initial conditions. When they say y of 1, well, we know that y is x of 1 of 0 is 1, and y prime is really x2 of 0 is 0. There it is for the first one. For the second case, I have 6 of them. Well, look at them. Y is really x sub 1 of 0 equals y prime, that's x sub 2 of 0. All the way, y sub 5, isn't that y sub 5 x sub 6? And all of these are 0. And in this case here, when I want to go for the initial conditions, I would say x is really x sub 1 equal negative 1. They have x prime is x sub 2 equals 0. They have y of 0, but y is x3, and that is a 1. And they have y prime, but that's x sub 4. And that's pretty much it. That's all we want to do in this section. Again, when the time comes, I will call back, remind you of this, and we will apply this when the time is needed.